Hi everyone, this is Hardik from fuzzing.in. Thank you for joining my live stream. Uh, in this stream, let us go ahead and see some of the heap related CTF challenges, understand how does heap works on Linux system, and we will work on solving few of the CTF challenges. So let's start. So hopefully you can see my screen over here, and let me just verify once more that it's working. Velocity of challenges. Okay, so that is let's fine. Start. It seems to be working, and now what we are going to do is that we are going to take some challenges which are actually on this website that is called exploit.education. So we will go through a few of the challenges. We will not download any virtual machine. We will simply download the source code and then we will try to solve them. So you can see that there are like different uh, labels. You can see Nebula, and there is Phoenix, there is Fusion, right? So Nebula challenges. Just 1 minute. I need to change some settings. Okay, so let me correct it. Okay, yeah. So what we are going to see now is few challenges from the Phoenix over here. So you can see that the description has been given that Nebula basically covers a variety of simple and intermediate challenges. It basically focuses on Linux privilege escalation and common scripting language related issue. We are not going to cover them in this stream. We might consider them in future videos or live streams. And Fusion also have some memory corruption, format strings, and Higgs exploitation issues. But these are suitable for like more advanced scenarios where you have uh, like understanding of how does heap work and all these things. So we will see that in a later stage. But in the Phoenix thing, it contains some basic like buffer overflows and format strings and heap exploitation, old style Linux system. So uh, also another thing to notice over here is that the challenges which are present here, they does not have any of the modern exploit mitigation system enabled. So we will not be using any exploit mitigation bypass technique over here, but the objective and motive is to simply understand how does he work on the system and what are the issues and how can we write few of the exploits for them. So I have actually downloaded a few of these challenges on my system, and before we start, you need to set up your system for that. So there are few tools. In my case, I'm using WSL Ubuntu Linux distro. So I'll be using that. And you can use any of this thing, like if you have VMware or VirtualBox or Hyper-V, you can use any Ubuntu or any Linux-based distribution like Kali or whatever you want. And just give me a minute. There seems to be some issue. Okay. Okay, that is fine. So it was showing some error in the streaming, so that is fine. Okay, so now let us go ahead and set up the pawn tool. So first thing you need to install is pawn tools, and you can install it by simply running pip3 install pawn tools if you already have it, and if you want to reinstall, you can use this tag that is called force dash dash force dash reinstall. It will install pawn tools on your system, which I already have installed on my thing, and then you can go to this website that is called exploit.education, as I have highlighted over here, and you can go to Phoenix. So you can see that there are different challenges over here. It starts from like stack 0, stack 1, it goes to up to like stack 6, and then it starts with format 0, format 4. So there are like 6 stack based challenges, and there are four format string based challenges, and then there are, I think, okay, 0, 1, 2, 3. So there are four, and it starts from zero. So there are five format string based challenges and seven stack based challenges, and there are like four heap based challenges. So we will start with heap 0 over here, and we can see that the source code is given over here, and we'll first go through the code. We'll understand what this program does, and then we'll see uh, how can we analyze that. So you can see that this is a very simple program. There is a main function. Let's start with the main, what it does. So inside the main, we can see that there are two structure. Like first one is the structure which is of type data, and second one is the structure which is of type fp or function pointer. So these structures are declared over here. So if you see the data structure or the struct name data, right, it simply has one name string which is of 64 bytes, and the second one which is fp or file pointer, right, it has a function pointer which is which will actually point to a function later on. And then we can also see that there are two functions. One is called winner, and when you call this function, what it will do is that it will simply print a message that is congratulations, you have passed this level. And the second function, which is no winner, and what it will do is that when you call this function, it will say level has not been passed, function pointer has not been overwritten. So if we move forward, it simply displays one banner over here. Then it checks for the argument. So it takes like one argument. So that is fine. And then it does a malloc call over here. So you can see that it actually does malloc for the structure type data, which is like size of structure, which will be somewhere around 64 bytes. And the second one is for the function pointer over here. So this will be the malloc. So the size will be structure file pointer, or sorry, the structure will be function pointer over here. And now we can see that there is a string copy over here, which is d name. So what it does is that in the malloc which it is allocated over here, like in the data which is of 64 bytes, it will copy whatever argument we have given over here, as we can see it over here. And then it is calling function or the function pointer over here. So the function right now we see it actually points to no winner over here, and I think we need to call the winner function over here. So let me just see. Okay, yeah, okay. So now let us copy this code, and then we will see how it works. So let's go to heap 0, and I have already copied the actually code on my system. So same code over here, right? Uh, and one thing to notice over here is that for compilation, we need to disable all the exploit mitigation uh, techniques. So let me show you all the techniques. So we need to use some flags with GCC, and the first flag will be like no pi. So we can use this command like gcc heap 0.co heap 0. Then we can give the all the flags here, like no pi. Then we also want to disable annex, so we need to look for that. Disable annex bit for that also. Okay, I think this link will give the flag. So yeah, we can probably copy this too as well. So let's copy this. So right now we have disabled no pi, that is then we have like f no stack protector, and then we have like executable stack, and we can also disable reload. This is disable So I think we can use this thing, right? It will disable relocation. Okay, and then when you run it, I'm not running it because I have already compiled it and I have like few addresses in my exploit script, so we'll discuss that. So if we see over here, uh, okay, this is the binary which is heap dash 0. So let's understand this binary first. So we'll do heap 0 and we can see that it is a 64-bit ELF executable binary. And let's try running checksec on this first. So checksec is a it's a utility which comes with pawn tools, and you can run it on any file. It will give you all the mitigation or all the exploit mitigation technique which a binary is using. So let's use this for our binary and see what all are enabled. So we can see that the architecture is AMD 64 Little Indian, then relocation this is disabled, and stack canary we have disabled it, and exploit is also disabled, pi is disabled, stack is executable, and RWX. So all the exploit mitigation bypass technique has been disabled in this binary. And let us try running this binary now and see what actually happens. So when we run, it gives us a message that data is at this particular offset and file pointer is at or function pointer is at this particular offset. I'm getting confused with file pointer and function pointer, but that is fine. And we are getting a sec fault, right? So now what we can do is that we can use gdb, and we can use this command, that is gdb dash args and heap 0, and we'll see how this particular binary works, what it does. So we can set a breakpoint on main function and we can run it. So it will take some time, but yeah, okay. So we can see that the source code is displayed over here. This is the assembly code, and these are the register, and this is the call stack. So let's do one thing. We will first run this command, which is like a visualization of heap. It will give you if there is any heap. So right now we can see that there is no heap allocation which has been made by this binary. So heap is not initialized yet, but our allocation will happen in the like when we use this malloc over here. So let's use and command, which means that execute this line. So now we can see that the malloc has happened. So let's do this again, and we can see that heap has been allocated and it has been like it is having different colors over here. So you can see that the heap which we have allocated, it's coming over here. So this is actually 51. The size is coming as 51, but actual size will be 50 because the 1 byte will be used for some flags and any other things. So you can see that it is set to 0, and if you calculate the size, right, so you can see that the total size will be these 8 bytes, and it's up to over here. So 8 plus 8 plus 8, so these are like 16, 16, 32, and this is 64 and plus 8 plus 8. So this is total allocation of 80 bytes. So 80 bytes, if we see in hex, it will be 50. So let's uh, verify that first. So I'm using 80 and will show that it comes to 50. So 1 byte extra over here is for the uh, different flags and all this thing kind of thing. And now actually let me start Python. Okay, anyway, so this is the memory which is allocated in the heap. Now let's press n and see what's going on. So we have allocated another memory on the heap over here. So if we do again this over here, we can see that this block in the green, what you see over here, is the newly allocated memory. And again, if you calculate the size for this, like this will be 8 bytes, 8 plus 8 plus 8 plus 8. So it should be around 32 bytes. And you can see that the actual size mentioned over here is 21. So 1 byte if you remove, it will be x20. So if we convert x20 to decimal, it will be 32 bytes. So yeah, so this is what the total allocation size is over here. And now let's again move forward with this code, what it does. So when we do next, what it will do is that it will print the address of uh, this malloc, first malloc and second malloc, as we can see it over here. So that is fine. So we can verify if we see our first malloc is, it starts from 4290 and the second one comes from 42E0, right? So if we do and we can see that it might have printed that over here. And then what it will do is that it will do string copy. So uh, the d dash name, right? This is the structure which contains the name variable, which is of 64 bytes. So it will copy all the data over here. So let's wait and see what happens after this uh, string copy. So right now let's see the heap. We can see that there are some new bytes which has been added over here, and these are this is our original buffer and this is our second malloc buffer. This contains a function pointer over here. So this is the function pointer over here. This is the function pointer which we are using. So let's wait for string copy, and now we are getting a 6 save, that is segmentation fault over here. So let us see heap, what does it contains. And we can see that right now uh, nothing is over here. So let's hit continue and see what is going on here. We can see that it's crashing because there is a string copy call and I think there is no data over here. So let's do one thing, we will again run it. Let me quit. And what we are going to do now is that we will actually give some argument to our binary, and we need to figure out what is the length. So what we can do is that we can use on tools cyclic tool, and what this tool will do is that it will generate some random pattern, and we can use that. So let's generate a random pattern of say 50 bytes. Yeah, that is fine. So we will copy this pattern now, and let's again give argument. So we will use this pattern and let's run it again and see what happens. So okay, and let's do next. So let's do run. Sorry, I need to. Okay, so if we simply run it, it will give a message that label has not been passed, as you can see it over here. So let us go ahead and increase the size of the buffer. So let's generate cyclic like 80. We will again copy this. Let's actually do one thing. We will generate 100 bytes of buffer because we are allocating 64 bytes, so it should be more than that. So override the next buffer, right? So yeah, okay, now let's copy and paste this 100 bytes of data. There is some issue. Okay, so let's see what happens now. Let's run it again, and we can see that the program is crashing over here, and it is crashing because it is trying to call RDX. And if we see what does RDX contains, so RDX has 6161 some bytes over here. And what we can do, if we check over here, right, so this is the ASCII representation of this byte. So basically it is overwriting this particular register, and then since this is a function pointer over here, it is calling, but there is nothing at this address. So this is why our program is crashing. So now we need to figure out what is the length of buffer by which we can figure out, we can overwrite this RDX. And what we are going to do here now is that since we can overwrite any of this. Someone is sending a message. Hi, Kosh. How are you? Thank you for joining the stream. No, I'm not fuzzing. I'm just trying to solve some TTFs for heap related overflow. So what we are going to do here is we can actually change, we can take the address of our function winner and we can pass it to this argument and we can overwrite rdx and we will call this function. So what will happen, our uh, winner function will get called and we will get this message. So that is how we solve this particular challenge. So now we need to figure out what is the length of this particular buffer. So let's do one thing. So we have already copied, we can actually copy this ASCII contents and we can figure out the length. So let's quit and we can write cyclic dash l and the content which we have. So it will give us the length that at which offset this will start overwriting the heap buffer over here. So if we write anything after 80, it will start overwriting our RDS register over here. So this is first thing. Now we know that there is this particular length. So let's do one thing. We will generate another pattern like cyclic 80 and we can verify that this length is proper or not. So this is a 80 byte pattern which we have generated and we will again use gdb dash dash arg. I have copied this 80 bytes data and now let's see if our theory is correct or not, that we need 80 bytes to overflow this particular register rdx, right? So let's set up a breakpoint on main and run. So we will do next again. Okay, so here it is like changing the function pointer to no winner function. So if we run this, we will get that our exploitation is sorry, our yeah, exploitation is not successful, right? But we need to change it this no winner, right, which you see it over here, to winner. That is what we are trying to do. So now let's do one thing. We will continue like next and we have given our like 80 bytes over here. So in the next string copy, this will override this particular dname over here, right? So if we again do a viz which will show us the heap visualization, you can see that this is the buffer and right now it is empty, right? And this is where it contains the address of the function. So let's do one thing. We will do next, it will call string copy now and it will override. So let's do this over here and we can see that some corruption has happened because suddenly it started showing a lot of heap data, right? Heap size has become very large. So it gives a message that we can set max visualize chunk size to 0x500. Let's set it and see. So it will actually help us to avoid this much scrolling. And now let's again do this. So yeah, so you can see that it directly jumped over here. So and we can go to the top. So this was the buffer where it contains a 000 before the string copy. But when we call string copy, you can see that it has actually overwritten everything over here. It has also overwritten the next heap header. So if you recall, it was like 21 bytes over here. Let me see if I can show you if the scroll history is proper. I can show you that. If not, then we don't have any other option. So yeah, like over here, yeah, you can see that actual value was 21 and it contains some flags and the length of this heap chunk. So this heap chunk length, the heap chunk which you see it in the green, right? So if you modify this length, what will happen? It will cause the corruption and your heap chunk length will become very high. So that is what is happening in this case, and that's why we are seeing this much new heap data over here, right? So if we see over here, we can see that it is overwritten this, and this will become the length. So the actual length will be like 72 over here, because if we like remove one byte, so the actual length will become 6161, then 72 over here. So that big of this That will be the length of this particular heap is. So this is what we have done, and now let us do one thing. So we can see that some overflow is happening here, and now right, some message is coming on the stream. So looks like there is hello. Looks like there is some issue with my microphone. The battery went down, and therefore you guys were not able to listen to me. So I think at what uh, when did you lost? Can you someone just type it? Are you able to understand this GDP pawn tools thing which I mentioned? Okay, wait, just give me a minute. Let's see. Hold on. So you can hear me now, right? I fixed the issue. Okay. So what? Okay, thank you. So we can continue. So what I have done over here is that I have used a tool called template, which comes with pawn tools, and I have given the executable name over here, which is heap0, and then we have redirected the output to exploit.py. So it generates a exploit.py, and when we open this exploit.py file over here, we can see that it contains a basic structure on which you can build your exploit. So it simply imports everything from the pawn tools, then it actually create a variable of exe over here, then it takes it actually has a start function over here. So it checks whether we have given gdb, capital GDB in the argument. If so, then it will call gdb. If we have not given, then it will simply launch the process. So in this case over here, if we give gdb, then it will call it gdb script. So this gdb script is over here, and this is a very simple gdb script. What it will do is that it will set up a breakpoint on the main function. So whenever your binary gets launched, it will break on the main, and then it will continue over here. And these are the comments, and then it will simply start io equal to start, and then io interactive. So we can modify this to suit our needs. So let us go back to our original exploit code over here, and you can see I have removed all the comments and all the unnecessary things and simplified this. So in this case, I have not changed anything. I have simply renamed it that exe to elf, and then over here, uh, what I have done is that I have actually used a variable called payload, and as we know that the length we want here is 80 bytes, which is in decimal. So if we convert it to the hex, it will be 50 bytes. So I'm simply doing a byte object over here. It is specific to Python 3 and Python 2. You don't need this, so we need this. We need to use this b over here. And what it will do is that it will basically create a string containing 80 characters. And after that, we are using p32 and then elf.symbols winner. So what this will do is that we have already created a elf class over here, right? And what it will do is that it will try to identify the symbol, and it will get the address of winner function over here. So you can either give that address manually. You can use this command like nm you can figure out that address and you can hard code it over here. But this is, I think, the good thing about pawn tools, that you don't need to do that manual task. You can simply call this function elf.symbols, and you can give the function name which is present inside binary. It will give you the address, and what you can do, it will give you the offset, and then you can align it. So this p32 is to align for alignment, and it will add that to this particular payload. And then we are simply starting our binary with this function start payload. So in the start function, we are giving this payload. So what will actually happen, it will start our binary, and it will give this payload which we have created over here, and then it will run it. And then this IO interactive means just in case you want to do some kind of interaction, but since this is a very simple challenge, we cannot do much here. So let's do one thing. We will try to run this binary now and see what happens. So I will run it using, let's remove GDB first and let's run it. So you can see that when we run this, it actually runs checksec first. We actually don't need it, but that is fine. Then this is the payload, and the payload length is 84 bytes. So why 84 bytes? This is because uh, first we are using 80 bytes buffer, and the next 4 bytes, this will overwrite the buffer which we want over here, right? this thing. So it will overwrite, this 8 bytes will overwrite over here. So this is what we are doing. We change this address, which is 401100, we'll change it to 401196, so that when RIP instruction, RIP register uh, uh, try to execute, it will go to this address and then it will actually call our winner function. So this is what is mentioned inside the winner function, as you can see it over here. Yeah, over here. So I think my source code file is a bit older, so there are some slight changes over there, but that is fine. So we can see it over here, and this is the message which we are getting over here, right? So it means that we have successfully solved this challenge. And now one more thing we can do, let's press any key. We can see how does it look like in the GDB, how can we debug this kind of issues, right? So what you can do is that, since we are using pawn tools template, let us simply give a argument in capital, that is GDB over here, and see what happens, right? And we will also see some heap related concepts now. So when I run it, you can see that it starts a new terminal, which you can see it over here now, right? And this is basically a telix, which is a terminal, and when you run pawn tools, when you give GDB, it start this. I have customized it to suit my the overall theme and all, so you can see. And now as we can see that it breaks at main function, and I will see if there is any message over here. Yes, Kuch. So it is 80 bytes plus address of winner function. So if you are using a x86 binary 32-bit, it will be 4 bytes. If you are using 64-bit, it will be 8 bytes. So yeah, that is the address of winner function. And now, as you can see over here, let us first see if there is any memory which is allocated. So there is no memory. Let's do and. So and now we will again do this. So we can see that this memory is allocated, this chunk is allocated over here. We will see what these bytes are, what these bits are in short a while. And let's do next again, and you can see that now our second instruction is also second, this line is also get executed, and we will have two malloc now. So we can confirm it by typing this command, and we can see that yeah, so this is first malloc and this is second malloc over here, right? So this contains the name variable, which is of 64 bytes, and this contains the function pointer address, which actually is for 8 bytes, but with all the heap data structure and all, it will allocate it for like 32 bytes over here. 1 2 3 4. So these are 8 bytes, 8 by 4, 32 bytes. So that is fine. Now let's do next, and yeah, so you can see that right now we have not overwritten. Okay, yeah, right now we have not overwritten, and we will call string copy. So after string copy, we'll see what happened. So let's do viz again. Okay, and as you can see that we are getting a lot of heap data over here. This is because some corruption has happened, and therefore we can use this command, set max visualization size 0xf 0x500, and then we can again do this. So this will help us simplify things. Yeah, and now you can see that with the 80 bytes of data we have overwritten up to here, right? The second heap, it was 21 bytes, as we can see it over here. This was, it's too big actually. Yeah, over here. I think this is also overwritten here. That is fine because it's too big, so that's fine. So we have overwritten that particular address, and now when we run it, let's actually do next. What it will do is that the function pointer value, right, the fp value which is in the second heap allocation over here, over here. This value will get assigned to the function pointer, and this is the address of winner function. So if we continue, it will actually call our winner function and it will display the message, and uh, that's how we solve this petrol challenge. So it is calling exit over here. So it means that we have completed this challenge over here. Now what we can do is that let's run it again and understand some of the heap data structure. So yeah, let's try to run it again. And if we click next, now if we do this, right, we will see that this allocation is done over here. But what are these bytes? What does it contains? What is the structure of heap? Why this is like 51 and not 50? So for that, what we can do is that there are some memory structure which we need to check. So let's see if it's there in my command history, or yeah, I think it should be there. So that's fine. Yeah. So there is a pointer uh, which represents a structure that we can use. So we call it chunk pointer. This is the data structure. If you want to understand what this heap bytes are, what does it contains, right? So we can use this, and let's use this address. In my case, it is F2290. So let's use this address. I will simply copy it, or run at F2290. So you will see that it display all the heap related metadata like chunk previous size. So what is the size of previous chunk? It is 0 over here. Then what is the chunk size? So what is the size of this particular heap chunk? So it is coming is 81. This is because there is one byte which is for various flags. So this is 81. Then forward pointer. So this will be the forward pointer. This will be backward pointer. And how we can figure it out is we can simply print it. So let's do print. We want to see the address, right? So let's use variable one, and let's verify it with chunk underscore previous size. So it is showing 0, and if I print the address of this variable, let's see what we get. So we get, so this chunk previous size, right, which is mentioned over here, it is at address this thing. So if we look at this address where it is F2290, this is the address F2290. So this will be the size of previous chunk. And if we print the address of say next variable, that is chunk size, right, we just want to make sure that the variable which we are seeing are proper. So first let's print the value chunk size. So it is coming 81. It means this, which is correct. And now let's print the address of this variable, so we can figure out that what are these bytes. So the address is coming is 2298. So 2290 is over here, and 2298 starts from here. So this is the size of this heap chunk, right? And similarly, if we go forward, what we can do is we can figure out the address of FD. Where does it resides in this entire heap chunk, right? So which byte actually denotes this? So let's use same thing. We can simply use FD over here, and it will give us the address. So it is 22A0. So these 8 bytes, this belongs to FD pointer. And similarly, we can do it for the BK. So let's change it to BK, and we can see that we are getting A8 over here. So the address over here A8 means this bytes. So this belongs to this backward pointer, what you can call over here. And similarly, if we see FD next size, now let's figure out which of these bytes or which of this address which actually represent this FD underscore next size, right? So let's simply do the same concept, ft underscore next size, and you can see that it is denoted at address b0 over here. So b0 is over here, and if we see the next size, bk underscore next size, right, same thing, bk underscore next size, it is at address b8, so b8 is over here. So this 4 bytes, if this heap is not in use, then this will be used, but if heap is in use, then this pointer will not be used. It will contain the data over here. The data will start from here to like end of the heap over here, right? So this is a difference. If your heap is not in use, then this will be used as a pointer, but if your heap is in use, then this will contain the data over here. Right now, this is how you actually uh, analyze various heap related metadata, and we can actually do one more thing. Let's try to solve second challenge as well. uh, for 2 to b0, it's not gonna be complete. It's just only the first value which will be, yes, it will be 0 0. It will automatically, if you don't give, it will be 0 0 over here. So that is how it works. So if you see the exploit, right, I think our file is 64-bit over here, and if we see our exploit script, you can see that we can actually, we are giving p32 and not p64. Actually we should use p64, but this will take the address and initial bytes will be 0 0. So it's like you are having 0 0 4 0, so it will take 40 over here. That is how it will work. So let's do one more thing. We can actually try second challenge as well. So let me go to heap open, and let's see what does it contains. So this is the uh, first challenge, and you can see that it is slightly different than the first challenge which we have seen. So here you can see there is a heap structure which contains one integer variable and one character variable over here. Now there is no limit on character. You can do whatever malloc you want to do, and there is an integer variable, right? And then inside the main function, what it does is that it is creating two instances of this heap structure variable, and then uh, it is actually allocating memory for them. Then it is setting priority as 1 for first one, and it is again doing malloc of 8 bytes for the name over here, right? So same, it is creating two such variables, two such structures, and then it is copying, it is doing string copy. So in the first name, when you create two variable of type heap structure, inside first it will copy argv1. So the first argument which you will give to the program, it will be get copied to the first variable name, and the second argument will get copied to the second uh, name over here. So we are getting two heap structure over here, right? And then it is simply calling printf that and it displaying a message, and that's a ref outside. So we can also see that there is a winner function, but it is not getting called anywhere. So the challenge over here is that how can we use this heap related data, and how can we exploit it, or how can we change it so that we actually get this winner function getting executed. So all these challenges are type are called like return to win. So let's debug and see how does it look like first, and then we will see how can we exploit. So again, I will actually run Python. Yes, what is that question? Uh, so first let's see what our file is. I have actually compiled this file, And let's see. Okay, it is a 64-bit file. Let's do check sec, and you can see that all the mitigations are disabled in this binary as well. So we can actually run this binary with ourselves before running it in GDB, and let's see what happens. So it gives segmentation fault. Okay, let's do two parameter AAA and VVV. So okay, so if we give two parameters, it gives this message. So no, there is no conference which I am aware of in Bangalore. I just wanted to meet you people who does fuzzing, and that's why I sent this message on the Discord. So if you are in Bangalore, let me know. So now let's move ahead and see how can we exploit this second challenge. So let's try running it in GDB first. So I will simply use this command gdb arg, or I think I have Python script as well. So that actually opens the Telix terminal, which I think I prefer more. So okay, so this terminal will get opened over here, and we can see that it breaks on the main function. Now what first we will do is that we will try to understand how this heap is getting allocated, and how can we actually utilize various feature, or how can we misuse various features. So let's do one thing. Let's do this as always and see if there is any allocation. So there is no allocation. Now let's do next. So uh, okay, I think first allocation has happened. So we are allocating the memory for the heap structure for I1 over here, right? So let's see. So this is 21 bytes over here. So this is the first I1 variable. Let's do next. So the value of it, like priority, will be 1. So let's see if we can see that in our visualization. Yeah, it's over here. So this is the value which is set to 1, and this value, this is the pointer, right? So let's do one thing. See, this is empty right now. So let's do next, and what will happen is that it will actually do a malloc for 8 bytes, right? And it will assign that to name. So that malloc address which will return, it should be present inside this name value, and we can verify that if we again type this over here. So we can see that this is the address. So this is the address which is written by malloc, and it is pointed by uh, this particular variable name. So if we go to this address 1A47260 over here, yeah. So this is where the malloc data will start. This is another heap chunk, and interesting thing you will notice is that this allocation has happened after our, like, first we did allocation for this structure, and then we did it for name. So the allocation is consecutive. If we overwrite anything over here, it will move to the next header. We can corrupt it very easily, right? But we are only having integer over here, so that will not happen. But if we go to this here, it points to a buffer of 8 bytes. So this is 8 bytes over here. These are the 8 bytes. And if we overwrite this, right, so it will overwrite the next available chunk. Right now it is top chunk, but we have not done entire allocation. So let's move next. And now another malloc has happened for the second variable, that is I2. So if we see now in visualization, we can see that after this green, this allocation has again happened. Now again you can identify the variable. This is the priority, and this will point to the name variable, right? So if we see it over here, the priority will be set to 2. This is what we can see at the heap memory, and this malloc will return address, and it will be set like set into that heap. So let's do next so that our malloc get executed. So it has allocated 8 bytes now, right? So now what we can verify is that the 2 and this address should be present on the heap. So if I do this, yeah, so you can see that this is the structure, right? This is the entire structure variable. This is the priority variable, and the value of it is 2, and the value of the name, which is allocated by malloc, it points to this particular memory location, that is 4a, oh sorry, it is 1A47300. So it is over here, right? So this is what the buffer is. This is the 8 byte buffer second. So you can notice the allocation happens consecutively, like we have first structure, then this is the malloc for the name, then second structure and the malloc for the name. If we overwrite any of this name buffer over here, this thing, right? If we overwrite, we start filling over here. Since this is only 8 bytes, it will overwrite the next heap length and the structure, and we can overwrite this variable here as well, right? So let's see what happens next. Now next you can see that whatever argument we have given, it will be stored in that particular location. So that is for argument 1 and this is for argument 2. So I will do next one more time so that both the string copy will get executed. So now you can see that we have given few arguments and that should be present in the memory. So let's do this again, and you can see that corruption has happened, right? So that's why we are seeing this many heap related data. So limit the visualize chunk size to 500, and let's again do this so that we can see the memory now. And you can see that this was the first allocation, right? This is the address of first malloc for the name, which was of 8 bytes. So that 8 bytes were this up to here. But what has happened is that inside the script, I have actually given data which is more than 8 bytes, and that has overwritten the next malloc header, the next chunks header over here, and that's why the size and everything has been changed over here, right? So in this case, uh, what has happened is that uh, the argument which I have given, that is overwritten the second mallocs, and that is causing this corruption. So let's do one thing. We need to figure out the length, right, by which we can overwrite. So again, we will use cyclic pattern, and let's generate 100 bytes of buffer again, and we will run this binary again, heap 1. I will simply copy paste this buffer over here, and this is first parameter. I need to give second parameter as well. Actually, something happened. Wait, some issue with the paste. That's fine. So this is first, and I think that copy paste is having some issue. Okay, hopefully this should work now. Yeah, okay. So this is first argument, and let's give second argument as bb and see what happens in this case. So Kush, okay, I don't know which location you are, but so there might be some conference like these sites, or I think that happened recently. You can come and attend that. Okay, so let's run it now. Actually, let's set a breakpoint on main first, and let's run it now and see what happens. Right, so we can actually we can simply execute it and see if we are getting any crashes. Okay, yeah, so we can see that we are getting a crash in string copy, and this is because uh, so when is besides Ahmedabad, I'm not sure. but I can try, not sure right now. So we can see that this dereference, right? The error we are getting is cannot dereference. It means that it is not able to access this particular memory location, which is inside RDI. So RDI contains this bytes. Now let's figure out the length by which we can see that this is getting overwritten. So let's do cyclic and dash L and okay. So the length which we are getting is 40 bytes. So what does it means is that if we give 40 bytes in the first argument, it will overwrite our uh, it will overwrite or it will cause us dereference error. So let's generate an input which is of 40 bytes and we can verify this theory. Okay, so these are the 40 bytes input and same command gdb dash dash args heap underscore 1 and this 40 bytes is over here and let's give bb 4 bytes and see what happens now. And let's set up a breakpoint at main continue, oh sorry, r, and we are at malloc. So let's click n. Okay, so this is where the corruption will happen. Let's see the heap first. Okay, this is our uh, first this thing. So this at this location will be our uh, malloc pointed string and it should be over here. So the overflow will happen over here. These are the 8 bytes and this is 16, this is 32 and over here. So I think this will overwrite. We want to overwrite over here. This is what is going on in the uh, RCX or RDI which we have seen. So let's see. So I will do next. Okay, it has overwritten. Let's again verify. Okay, the corruption has already happened. Let's set max visualize limit to 0500 and again do this and see what it has overwritten. So yeah, you can see that these are the 8 bytes buffer and it has actually overwritten the header of next buffer and uh, next 8 bytes as well, right? So this is correct. So let's do continue and see. Let's do max actually and see what happens. Okay, so it is not overwritten and it will easily. Okay, so we need 4 more bytes over here. So let's do one thing. I will use previous command. I will simply write AA over here. Actually it's 64 bytes, so I need to use 8 more bytes. Yes, so this is the payload which I am sending. I have simply generated is using cyclic. You can generate any 40 bytes payload. Actually it will require 48 bytes to overwrite. So let's put a breakpoint on main and run it, and again we will do next till string copy. Okay, we will see visualization. So this is first, this is second, and this is the buffer over here. This is 8 bytes, but what will happen if we give it like 48 bytes? It will overwrite up to 8 16. This is 8, this is 16, this is 32, and over here it should be able to overwrite up to here. So let's try doing next. Okay, and let's verify. So same set max visualize limit 500 this again and see what happens over here. Yeah, so these are the like 8 bytes data. Then it is actually overwritten over here, and then the AA which we have given Yeah, so this is the byte which actually it is overwritten, right? And now let's see what happens. So we'll do next, and we can see that we are getting this error, that is cannot dereference. So we actually need 48 bytes of data in the first parameter, first argument, and when we do this, it will actually try to access this data. And you can also see that what it is actually doing. So RDI contains this address where it is trying to write some data from the ECX. So this is happening because of second string copy. So our first string copy has done this corruption, and inside the second string copy, it is moving this data. So it is actually a write where I mean, so you can actually control this location. If instead of 414141, I give some address, right? And if I control ECX value, so if you see ECX contains 4, okay, over here. So the ECX or RCX, it contains the second parameter. So what is happening in this case is that the first parameter gives you some location which you can control, and the second parameter will give you the bytes which you can write on that location. So it is something you can write few bytes at a arbitrary location over here, or arbitrary address, right? So okay, so in that case what we can do is that we can actually use something like uh, okay, so if we see the code, okay, I think there must be some call to another function, so we can use this got override or PLT related thing here. Let me do, let's exit. Okay, so we can understand that what this vulnerability is, that the first parameter, you can control the location, you give a location, and the second parameter, right, you can write that particular value to that location. So let's do one thing. We can actually run this again, or let's set up a breakpoint on main. We'll run it again, and just want to see what is going on here. So I done next. Okay, so this is first string copy. This will overwrite this name buffer, then this will like overwrite next heap chunk as well, and inside the second string copy, okay, it will try to overwrite to that particular location. Okay, got it. So now what we can do is that if we change the address to our winner function, then uh, we can actually control the execution. So what we can do is that we need to call that address as well, right? Because by simply overwriting we cannot do anything. So we can see that there is a printf function over here, and in Linux we have this concept of I think got. Let's see. So yeah, so it is like, it's called a global offset table, and what it will do is that it will actually it will have the address of printf function. So yes, okay, over here. So we can simply use got, and you can see that it has printf function, and which is at this particular location. So if we override this address with the address of winner function, then when this printf will get called, actually it goes to this location and then we can execute winner function instead of printf function. So if this printf function was not there, then we might need to use something different, but this will make things easy because we have disabled all the mitigation protection over here, so that is fine. So now let's see how can we override this address actually. So I think plt is there or not. Okay, so let's quit, and what we can do is that we can search for printf function over here. Yeah, so if inside the binary if we get, okay, it's not coming, I think we have to use obj dump heap 1, and then let's see if we get the address of printf. Yes, okay, so we got the address of printf, which is over here. So if we write this, right, then 4010A0. Okay, so this is the address of printf, and we can see a call here as okay. If we can override this address, so this contains the address, right? So uh, yes, so let's do one thing. uh, we can override this address. We write the address over here. Yes, so we see the exploit. Four zero 8388. Okay, it should be actually put as, because that is what it calls. Okay, so let's see if this works or not. Yes, okay, it is working fine. So okay, so what we can do is that we can start crafting exploit for this as well. We'll simply use template heap1 and exploit.py. So in my case, I have already created this exploits. So let's see. I think I have this over here. Yeah, okay. So you can see that the uh, exploit is very simple over here as well. Same syntax. We are importing everything from pound tools. Then we are setting up the context, and then we are getting this ELF. Hey Alexi, how are you? Kush, what is Ryzen? I'm not sure. So yeah, so this is the exploit code over here, and what we are doing is that we are simply grabbing the address of put as in this. So we generated the 40 bytes of payload. We have copied it over here, and then this is the put at address. So and then this is the address of winner function. So let me show you actually what we can do. Is we can do R or something. Yeah, 403388, and the same thing we can do. We can find the address of the winner function. So this is the address of winner function, that is 401275. Right. So what we are going to do is that inside the parameter 1, after 40 bytes, we will add this address 403388, and during the second string copy in second parameter we will give this 401275. So this address will be written at this location, and when this printf function will get called, it will actually call our winner function. So that is what we are doing. So 403388, yeah, okay. So you can see that here it's in the Little Indian order 403388, and if there is any previous zero and all, we are not using it. If you use zero here like this, so if we use zero, this might cause some issue with your script and all, it will not work. So that's why I have not used zero over here. And you can also see that address of the winner function over here 401275, and then we are simply starting it, start payload. So there are two elements, actually it should be named is arg1. I don't know why I changed it to payload. Okay, I think I have copy pasted, so that's why I forgot to change. So let's change it to arg1. Okay, here also I need to change arg1, arg1, and okay, here as well arg1, and okay, this is actually not needed. Let's remove it actually. So this is the exploit. I have added comments as well. I think I will do one thing. I will copy paste this to my GitHub repo so that you can try it out. I will actually add compiled binary as well, because if you compile yourself, this address of return function of this will change. So I need to actually add compiled file as well. Okay, that I will do after this streaming. Once it ends, I will. Okay, payload. So here also I need to change. It's arg1. Okay. Hopefully I have not missed anything. Let's try running this again. Okay, yes, so we can see that we are getting this message, congratulations, you have completed this level, right? And we can actually see the second challenge which we are trying here. Yeah, over here. So this is the winner function, and which we have called it over here. So I think uh, this gives you an idea. Let's do one more thing. We will actually debug it using GDB. So I will call my exploit file, and let's give capital GDB. So we are using pawn tools, and that's why we are giving this GDB argument, and we'll see that everything is working fine. How does it looks like at the heap level, and how does heap look like, and also let's run it. Oh, okay, I think I did not change the command. So I think I need to, okay, use GDB here, and we can see. So this is the source code we can see, and this has our payload, right? So let's do next because we are already comfortable. How does it look like in the heap? Malloc happened and the variable got changed. Second malloc has happened. Let's visualize. So I will repeat once more time. This is where the malloc happened. This is first variable which is set to 1. This is the second malloc address, and this malloc address is over here, right? And let's keep doing next. Second malloc happened, second argument also happened. So let's see, this is second malloc, this is the variable name, and these are the 8 bytes over here, right? And now let's do next. So it has done string copy, it has actually overwritten uh, the heap structure over there. So we need to actually set max visualization over here. So and then let's do this. So you can see that this is the overwritten address over here, right? 403388. And right now, if we go to this address, let's see what does it contains. 403388. So print 403388. Okay, and this is the address of actually uh, protest function. So now what we are going to do here, actually let's see how does it okay, this will goes to the second thing. So let's do next. Yeah, okay, now it might have been overwritten. So let's do this, and okay, so at this address it might have written that particular thing. So yeah, so here it is. So at this thing you can see that this is the address which is of the address of the winner function, right? So now when we do next, here this printf will get called, and this printf will actually call puts, and that puts will actually call this winner function. So you see over here, right? Yeah, but this address uh, it contains the address of the puts function, and this actually contains the address of winner function. So I think this prints the message and it will work. Yeah, I think we will not see it over here. So let's run this script again. And yeah, we can see that congratulations, you have completed this level, and it gives some time. So it took some time, but that is fine. So I hope that this stream has given you a basic understanding of how does a heap based CTF works, how can we solve it. And what I will do is that I will upload this compiled binary and Python code as well inside my GitHub repo. If you are not sure, you can check the about section. You can actually go through other videos as well. And uh, let's connect next time. So I will stop the stream now. Hopefully you have enjoyed this, and uh, please do like, subscribe my channel. That will help me to make more such videos, do more such live streams. And if you have any questions or comment, feel free to post in the comment sections. Till the next video, goodbye, enjoy. Thank you, Alexi. Thank you, Kosh. I'm not sure if you are still watching the thing, but great to see you here, and see you next time. So thank you everyone, and goodbye. uh, Bye. Thank you. Bye.